Is John McGregor, and he presents something about comparing the formulations of CCAM and VCAM and aspects of their performance.
Thank you very much. It's a pleasure to be back here at the PDEs meeting, and this is a particularly interesting one and very well organised. The talk I'm giving today includes some material from a longer talk I gave 2 weeks ago, but also some new slides. So there's a number of people here who've heard a bit of it. We've been working on cube models for 10 or 15 years now, starting with the conformal cubic model and now moving on to the mnemonic model, and I'll say a bit about the two formulations and show some comparisons. I guess I should say that the flux form non-conformal is a lot harder work than the semi-Lagrangian advective form, but I'll show you comparisons and why that's the case. So the original mnemonic grid was Sidorni in 1972, and that's fairly uniform, but you can make it more uniform by the equiangular transformation, which most people use these days. So I started off doing advection tests on that one back in '96 or so, and it was pointed out to me then by Jim Purser that there's actually a conformal version which is isotropic and so on, and you can use the standard type equations that you have in a polar stereographic grid, etc. So I switched to that one for some period. So that's how that looks. The view on a lat long projection. C48 48 by 48 on a panel with about 200 kilometre resolution. So CCAM is semi-Lagrangian advective form, 2-time level. An unusual feature is the reversible staggering, which I'll say a bit about, and I've kept that reversible staggering property in CCAM and in the newer VCAM. And I'll go into some detail about that. And I do have posteriori conservation of mass and tracer variables in CCAM, and I'll say a little bit about that. Physics is reasonably standard for climate models. We mostly use it for regional climate modelling. I should point out that's where our money comes from, but to take part in a number of global activities. Because it's variable resolution, you need to be pretty careful with the physics, especially cumulus convection. So we have our own mass flux scheme where we've gone to a fair bit of trouble to see that it behaves quite well at both small and large grid lengths. On the conformal cubic grid and on the mnemonic grid, all variables are located at the centre of grid cells, including the velocities, but during the semi-implicity or gravity wave calculations we transform to the Arakawa C locations, U and V as shown there. And I use a reversible technique which lets you go backwards and forwards exactly using a tridiagonal solver. I'll say a little bit about that in a moment. So that gives very good dispersion properties, essentially as for a spectral method or a vorticity divergence method. So the staggering, if we look at the unstaggered locations along a line, where these lines are here, we want to go to the staggered positions where the x's are, introduce a pivot point 3/4 of the way along, either be here or here, and then you can write simple equations. The pivot value in the 2-point formula be 3/4 of that value plus a quarter of that, or alternatively 3/4 of that one plus a quarter of that. Or for a 3-point formula you get this type of formula. So you go from the staggered values to the unstaggered by this tridiagonal system, and because you're going around the 4 panels of the cube, it's a cyclic situation, just along a line to get the U's or another line for the V's, and can be solved by a cyclic tridiagonal solver, but I have an iterative solution which converges quickly and is better for MPI purposes. If you do tests on the shallow water equations, like following Dave Randall's study in the 90s, you can see the behaviour for both large radius of deformation or small radius of deformation. The continuous case, that's the x direction, the y direction, out to 2 delta x waves. That's the sort of behaviour you would like. The A grid does that, which is a bit rather too flat. C grid is pretty good. Z grid of Randall vorticity divergence is essentially the same as the C grid, and so is this reversible grid for this radius of deformation. If you go to small radius of deformation, again that's the good one. This one has an asymmetry, but that can be removed by alternating the location at pivot point periodically, and then that averages out to give that same response pattern. Just to show, 2-grid waves are preserved fully, so it's quite a lively transformation. There's no damping of the waves. There's a shifting of half a grid length for 2-grid length waves, 3-grid, and so on. So it preserves the amplitudes of those waves. I'll just mention in a semi-Lagrangian model you can do a number of tricks which are not available in the flux form, unfortunately. And the pressure gradient term in the pressure gradient term has can have a topography or orography contribution in this pressure plus log surface pressure term. Sorry, I'm talking about something else there which is not really important. I'll go on. This is what I'm trying to talk about. In the semi-Lagrangian, you have an advection of the log surface pressure plus a divergence term. The log surface pressure has this orography contribution, so you can split it up into the 2 components and do the regular bicubic type interpolation of the upstream values of log of this combined quantity. But for this extra term, you can do a bilinear interpolation, and that then is essentially exact interpolation if you regard your topography as being a linear interpolation between the various spikes. So this final upstream value of the log surface pressure is this bicubic contribution plus this essentially exact orography contribution. So that's convenient, but not available for the flux form version. And similar for temperature advection, you can break it up. The temperature has an orography contribution near mountains for some typical reference temperature profile, and again the total upstream temperature or advected temperature can be done as this bicubic component, and then a bilinear interpolated value for this orography component. And those 2 techniques mean I can get away without hybrid coordinates in the CCAM case. Unfortunately for VCAM, I can't do that, so I need to use hybrid coordinates. Conservation was talked about yesterday. I have my own scheme, which I'm very happy with. The main thing here is that it's monotonic, but the correction is related to the dynamics increment during that time step. So the largest fix-ups occur where there's been the largest time step during the last time step. We have it well implemented for message passing or MPI. So within each memory in each CPU is arranged as one long vector. So the physics is being done at all those points. Then we have the the halo region, north, south, east and west. And we think it's pretty good performance. So this red curve here is going up to 288 processors, so a speed up of about 210. So that's seems reasonable to us. This one is a different decomposition of the processors phase setter, but that's the usual one. VCAM, the new one, is on a curve on here. I think it's this. It's very hard to see, but it's a little bit slower than CCAM. Keep an eye on that clock. So we periodically run AMIP type runs just to check that the changes haven't done anything nasty. And for variable resolution, we need to refine the physics or improve the physics from time to time. But we try to keep the physics the same overall resolutions, have the occasional delta X dependence in the physics, and then go back and rerun the standard AMIP type run to make sure that the physics changes haven't messed things up. Here's an example of variable resolution. We do it by the Schmidt transformation, which is 1975, and we just move a panel over the region of interest, and then it's a zooming operation applied on a axis out of the page, and this is a zooming by a factor of 3. So the original 200 kilometres goes to about 60 kilometres over here. As people probably know, it preserves the orthogonality and isotropy of the grid. So it's the same equations, you just alter the map factor. And you can zoom quite strongly, and this is a fairly extreme example where we've zoomed the same number of grid points down to 8 kilometres over New Zealand, or down to 1 kilometre, and looks okay if you look up close, but nothing much happens in the northern hemisphere in those ones. So we have a side interest of doing sailing forecasts, and so that's a hobby we take part in. When we do those sort of forecasts, we would run the 60 kilometre first, and then that drives the course region of this one, which drives the course region of that one. It's a bit like one-way nesting, maybe 1.5-way nesting. And we do the same sort of approach for the high-resolution climate modelling. So the final grid would be this one, 20 kilometres over Eastern Australia. Would typically do something like run a global 100 or 200 kilometre grid and use the broad scale information in this region. In this run would come from that model via a digital filter, not digital in time as Peter does, but a space scale, and a typical length scale would be the length scale of this panel. So features of coarser length scale than that panel would be coming from that run, and we've settled on that after some fiddling around over the years. And we also try to fix up the biases by the host GCM by using the bias corrected SSTs. We don't try to take all the raw fields from the original GCM, because that would introduce various inconsistencies. So here's a bit of a picture of the digital filter. It can be done as a sequence of 1D filters. And we have a paper showing that it's very similar to the 2D collocation. It's sort of you do it in a particular order to get the agreement. We do have a non-hydrostatic option in CCAM. It's a simple or a cheap one to run. It's based on the Miller-White proposal from some years ago, which approximates some of the terms in the hydrostatic equations, and it ends up being a modified phi calculation, and that can be absorbed into the Helmholtz equation of CCAM for zero cost really. Again, that's not available in the new VCAMs, which is a shame, but so just to show what happens with that, this is a global run, but it's extremely stretched, down to 500 metres over a tiny spot on the globe, and nothing much elsewhere, 35 levels, and this is the cold bubble test, which people have shown similar. So when it hits the ground, it spreads out, and you get the vortices. This is I think people earlier might have showed a 2D example. This is a 3D, essentially axisymmetric example, but you do get these little vortices going out in the non-hydrostatic version, but the hydrostatic version you don't get the same nice behaviour. I'd better get on to VCAM quickly. So this is the sort of grid we've seen quite a lot in this workshop. There are a lot more cube grids around these days, so that's good to see. The point here is that if you look at the contravariant component on the edges, those trace around in a continuous sort of direction, which is what you expect because those lines are all parallel to one another. So that suggests if you have values at contravariant components at the centre of these cells, and as you chase around this line here, you can use the reversible approach to get the edge values and switch back to the central values. I think that's out of order. So so that's why we might want to go to the mnemonic grid. It is more uniform, which gives you a few less issues for parameterizations. Reversible staggering still works, and flux form is desirable for trace gases in particular. I'm using a forward-backward solver now for the gravity waves, which turns out to be a bit touchy. I'm tempted to go back to semi-Lagrangian, but it is working, but it's much touchier than good old semi-Lagrangian. But it does avoid the need for the Helmholtz equation, and also because they're not using the Helmholtz solver, you can avoid these linearizing approximations that are made in the gravity wave terms of the momentum equations. So these are the standard sort of equations. Horizontal advection, we have normal components. I'm using a TVD type approach, loosely following Randy Levesque. So we have the fluxes at the edges, but there are transverse components from what's going on in the other direction there. So you have low order and high order fluxes at the boundaries, and I'm combining those with mostly using the super B limiter. For advection, rather than advecting these various contravariant and covariant components, it's the Cartesian components that I advect the U, V and W. I think quite a few people do that these days. Just to go through this forward-backward solution procedure, we have the forward-backward loop where we start off by, that's done in the staggered space, so we do the reversible staggering of these U's and V's. We then need to calculate the pressure gradient terms, omega, sigma dot and so forth, update all of those, but we need to go back to the unstaggered grid to get the Coriolis contributions, which is a bit of an overhead, and then comes the advection. So the main MPI is the overhead is this reversible staggering at the substeps. I'd better get a move on here. So basically works fine, but I have found I need to introduce hybrid coordinates. So without hybrid coordinates, you see some oscillations, for example, near the Andes, which don't like to go away, but with hybrid coordinates, that does get rid of those sort of effects. Comparing CCAM and VCAM, upper level winds are fairly similar. This is just a 1 year test for the 4 seasons, and exactly the same physics, again just a 1 year test. This is observed climatology, DJF, so we're getting pretty, we can get a pretty reasonable climatology with the Aleutian low and so forth. And over the tropics it's actually quite good, better than the CCAM was for that same year. But we are not as good in the mid latitudes for rains. If you look over China and so forth, China or some other parts, we're a bit deficient. If you look closely also, you can see some influence of the panel edges in VCAM. In fact, just south of Australia, below Adelaide here, you can see this bit of an effect here. So that there is a set of panel boundaries going on there, which I only noticed very recently. But and in fact, if you do some advection tests, I'm doing things in the wrong order. I've gone to the full primitive equations, then go back to the simple tests, but never mind. So this is solid body rotation going eastward. So well, here's a cylinder starting here and going all the way around the globe and coming back to here. That's the initial profile, that black line. It's fine in the near the equator, but when you go through the vertices, there's a vertex there and here and so forth, there's this strange reduction of amplitude in the southern part, which puzzled me. It's a 2D problem, but a 2D advection, but in fact it's caused by spurious vertical advection. I'm doing it in the full 3D model, and the staggered velocities are being calculated and producing a divergence, which is producing a vertical velocity. So if you look at the vertical velocities, that's indeed the case. So these, you see these spurious vertical velocities. There's a solid body rotation of velocities, so there should be no vertical velocity. That's going up to 0.03, but by more carefully calculating the pivot velocities near the panel edges, reduce that by about a factor of 8, and then the advection test is fine. So you just need to be a bit more careful with those panel velocities. I still need to redo the climatology, which I hope will help. Or maybe I'll just put up that summary of differences and leave time for a couple of questions. So thank you.
I was a bit surprised by your mesh refinement, because normally you try to move the poles as far away from the region of interest as possible. You seem to be squashing them. You've got 4 of your vertices, you're squashing over Australia.
The centre of the panel is in the middle of Australia. Those poles are just unavoidable. They end up there. The centre of the transformation is the centre of the panel. It's just they're brought in close. So in the mnemonic grid, you won't see this clustering near the vertices. The mnemonic is much more uniform, extremely uniform.
I think we have to move on. So let's thank John again.